Well, let's see. It's 1:20. We're here. So announcements, nothing really new. Homework 4 is due on Monday. I believe I've already postponed it in WebAssign. Someone would have let me know by now if I had forgotten to do that. But yeah, homework 4 is due on Monday, the regular time, noon. And yeah, that's it for announcements. So if there are no questions, we'll move right into the warm-up. So we've been talking about the advantages of large telescopes. In particular, we've been talking about optical telescopes, and this is not an optical telescope, it's a radio telescope, but the same principles apply. There are two advantages to using a larger telescope. One is light gathering power. The more collecting area you have, the more light you can collect in the same amount of time. And this telescope has a lot of light gathering power, radio light gathering power. But the other advantage is resolving power. Now, how much does the telescope blur things out, independent of atmosphere? And we'll see the atmosphere doesn't really matter in the radio. But let's take a look at this. And again, we'll be talking about radio telescopes in a little bit today. And this is one of the more impressive ones out there, the Green Bank Telescope at Green Bank Observatory in West Virginia. I've been going there every summer since 1991, except this summer I didn't go because of COVID. But yeah, I've seen this telescope over the years. I've seen this telescope being built over the years, which is fascinating because it's huge. It's the largest moving thing on land, actually. So I'll come back and talk more about it later. Green Bank Telescope, it has this parabolic shape, and it can maintain that shape to millimeter precision because of it has an active optic system. It can morph its shape whenever it moves, so it can maintain a parabolic shape to millimeter precision, despite the fact that it's almost the size of a football field. Well, it is the size of a football field, but in meters, it's 95 meters across. And this allows us to focus the light with wavelengths as small as 3 millimeters. That millimeter precision means we can bounce light that's a little bit bigger than that, so about 3 millimeters, and have it go to the focal point. So what is its blurring scale at that wavelength of 3 millimeters for a telescope that big in arc seconds? I'll give you another 20 or 30 seconds for those who just got here. Well, moving slowly, trying to see how many are here. We have 107 of you. So I always get a lower response rate on the math questions. This is your chance to practice. See if we can push it any higher. There we go. I'm gunning for 40. Almost there. Going once. There we go. Okay. Okay, I see a bunch of sort of the right numbers. So let's put up the histogram here. Yeah, most of you got 7.9, and some of you were off by a factor of 1,000. That would be easy to account for, and other various factors. But you got 7-point stuff. Just 7.9 times 10 to the minus. You all got different exponents there, but the answer is 7.9. Let's go through the math. So here's our equation, and I'll give you one that's...
Can you move the study, please?
Oh yeah, thank you.
Okay.
I'll give you one that's easier to use in the radio in a little bit, but we can use the equation from the optical, which is already in arc seconds. So that's the amount of blurring produced just by the telescope, not worrying about the atmosphere. This is the wavelength of the light that you're looking at. This is the size of the telescope. And that wavelength is in microns. So here's one of the tricks for this one, being able to convert from millimeters to microns. There are 1,000 microns or micrometers in a millimeter. So you take that 3 millimeter wavelength, multiply by 1,000, and we're talking about 1,000 microns. So this is pretty long wavelength light. In the optical, you're talking hundreds of nanometers. Here we're talking thousands of micrometers. Diameter is 95 meters. So you plug that in, you get 0.25 times 3,000 divided by 95. It's 7.9 arc seconds. And it doesn't sound great because in the optical, you know, the atmosphere, again, in the optical, blurs a scale of 1 arc second. But you may also remember that as you go redward, the atmosphere is less and less of a problem. And radio is like the ultimate in going redward. It's very, very long wavelengths. And so the atmospheric blurring doesn't matter at all, really. So you're limited by the diffraction limit of your telescope. You can see here, if you have a long wavelength, you're going to have a lot of blurring. And that's the challenge in the radio. It's just you're dealing with really long wavelengths, so you're naturally going to have a very large diffraction limit. The only way to combat it is to build humongous telescopes, giant diameter telescopes. But we'll get back to all that. Questions about that? All right, so last time we were talking about UNC observatories. We kind of covered the big ones. Well, we started with the campus observatory just for kicks, but the primary large research observatories were SOAR, our 4-meter diameter telescope in the Chilean Andes, where we have 17% of the time, and SALT, which is like a 9-meter diameter telescope in South Africa, where we have 3% of the time. Today, I just want to wrap up our other two systems, which are much smaller, but they're, including the stuff that I do, the Skynet prompt telescopes are very small, and Professor Nick Law has developed the Everyscope, or Everyscopes. There are multiple of them now, which is a completely unique telescope. Nothing like it has ever been built. And although these are small, they're unique in that they're fully automated. No humans necessary, except when things break. And if we do our jobs well, that's fairly infrequently. So, you know, you save a lot of, most telescopes you have to travel to the site. So that's a lot of time, a lot of money, a lot of effort, a lot of staying up at night. With fully automated telescopes, you can skip over all that. You just log in. If you're in the labs, you know this. You just enter your observations and you go away. And they come back all on their own kind of magically. So it's this new way of observing. It's very efficient. And we're trying to move to larger and larger telescopes. And even though these are our small telescopes, they're the ones that bring in the most research dollars. SOAR and SALT are big, and we do interesting science with them. But Skynet Prompt, which I do, and the Everyscope, which I'll show you in a minute, it's very cutting edge what we're doing, and so it brings in lots of money. Like between me and Professor Law, we raised $4 million this summer alone. So although they're small telescopes, don't dismiss them because they're small. They're very interesting in pushing the cutting edge in a different way. Let me tell you a little bit about Prompt and Skynet. And again, if you're in the lab course, you know a lot about this stuff already. Let's see, got this in PowerPoint format. And I don't want to try to, PowerPoints are funny. When you activate them, they go onto the other screen, which is not the screen that I'm sharing. So I'll just do it this way. You can see that, right? Okay. So this is our primary cluster in the Chilean Andes. Some of our original telescopes, which were 16-inch diameter, so 0.4 meters, so quite small. And here's me standing next to one of them for scale. I think I've shown you these pictures before, but fully automated systems. And we built them originally not for student use or for use by other astronomers around the world, but just for a single research mission, and this was to study gamma ray bursts. It's a type of exploding star, massive stars, maybe about 25 times the mass of our sun, or more massive. They end their life by forming a black hole. But as they do this, they go through a kind of explosive process where a lot of material is ejected along the rotation axis at relativistic speeds, like 99.999% the speed of light, which boosts how bright it is as long as that beam is pointed at you, which means we can see these things from super, super far away, even with small telescopes, but they don't last long. They fade very quickly. And so we had to learn how to do robotic systems. There was no time to get to the telescope and control it manually. You also get a type of supernova explosion, an unusual type of supernova explosion. And we talk about these objects in more detail in Astro 102. They used to be complete mysteries, but over the past couple decades, we've learned that that's what causes at least most of them. And so we built the prompt telescopes to observe these things automatically so we can learn about them. Now that beam of radiation, it's full of gamma rays, and gamma rays don't make it through the atmosphere. So NASA has, and other countries as well, but NASA has the best spacecraft up there for this. Right now it's called SWIFT, and monitors about a quarter of the sky, just looking for these explosions, and it does other things as well. But when it finds it, it sends the coordinates down to us, and then our telescopes slew into position. And this happens very, very quickly, between the spacecraft detecting it, analyzing its own data, sending the coordinates down, our telescopes getting those and moving into position. The fastest we've ever done it is 32 seconds from spacecraft to ground-based detection. And in that case, we discovered the most luminous object in the universe. I mentioned before we discovered the most distant. We've also discovered the most luminous object, and here it is, 32 seconds after the explosion. So bright it's saturated. I can't tell you exactly how bright it was because it actually saturated in our image. But here, the next handful of images, we're now minutes after the explosion, tens of minutes, and that's about 30 minutes after the explosion. So you can see they fade away very, very quickly and look just like an ordinary star. If you're looking the optical, you wouldn't know where to look to find that, but you got to use those gamma rays to be pointed in the right direction, unless you're like observing the whole sky and can analyze all that data very, very quickly, which telescopes are moving in that direction.
I have a quick question.
Yeah, go ahead.
Since that's like a bunch of light years away, does that mean that happened long ago and not while you guys were observing it?
That's right. 2005, and I think I mentioned this previously, so I'm not going to go through it over and over, but we discovered the most distant object in the universe, which is 12.9 billion light years away, which means it occurred 12.9 billion years ago, before the sun or the earth had even formed, and spent all, most of that time, that whole time traveling across the universe. Partway on that journey, Earth formed, and then life evolved, and humans, and we built telescopes and got a space telescope up there just in time to catch the light as it passed by Earth. So yeah, it's a way of looking backwards in time. That's one of the cool things about astronomy. We can actually study the past. In other fields like archaeology, they dig down in the dirt, they're studying the past, but it's kind of what's left over. It's a version of the past that has been ruined by the ages and just being underground and wind and weather and all that. We are actually seeing it as it was billions of years ago. We can't see what the local universe was like billions of years ago. There's a trade-off. If I want to see what the past looked like, I have to look far away. But yeah, you get a picture of everything. So with these are the prompt telescopes, and we've been upgrading them. So kind of our largest ones are now 24 inches. We also have a 32-inch telescope down there. And I've been taking the smaller ones and redeploying them around the world to different sites. So this is where we're currently located. We have our site in Chile, which has been down for COVID, but is supposed to open in the next week or so, reopen. And we have 8 telescopes there, so that would be wonderful to have open again, both for the professionals and for the student users. We have 2 sites in Australia, one in Eastern Australia at the National Observatory of Australia, and it was struck by lightning a few years ago, but I've raised the money to rebuild the site. I just can't travel there because Americans aren't allowed to go anywhere these days. And then one in the western part of Australia, which those of you in the lab have been using, Micron telescope. In fact, it's our only prompt telescope left in the Southern Hemisphere. We've also been building 2 of them in Canada, one of which is open and another one should open soon. And so these are the prompt telescopes. These are the kind of elite telescopes on the system that my team has put together, that I've raised the money for. But also other people have come to us saying, hey, we have systems that are similar. Can we put them on Skynet? And this is kind of an older animation. There are actually a handful more now, one in Poland, many more in the US. Got another one here in Australia, some in Canada. And and so we've learned how to control pretty much every type of small telescope hardware on the market. We've learned all of their failure modes, like 300 or 400 different ways that all this different type of hardware can fail. And we've learned all of it. We've coded Skynet to fix as much as possible automatically. And what can't be fixed automatically, we're notified of, and we fix either remotely or by working with people on the ground at these sites. We've also integrated a large, actually this is a small radio telescope, 20 meters across. It's 6 stories tall, 150 tons. If you're in the lab, you'll be moving it around in lab 7 and taking some data of the invisible universe. I'll come back, we'll use this today in class, though it is being serviced this afternoon, so the demo may have to be postponed, but we'll see. And these are kind of the basic stats on Skynet. We're evenly split between research and education, public engagement as our mission. On the research side, it's used for much more than gamma ray bursts now. Pretty much everything you can do with small telescopes is done by international consortiums, and they publish data once every 20 days. 5 times in Nature and Science, which are kind of the top journals in astronomy and in science in general. And we're also the leading tracker of near-Earth objects in the Southern Hemisphere. These are things that could potentially strike the Earth. And so we help determine the orbits, and NASA pays us money for that. And on the education side, we've had 40,000 users of all ages, elementary school through graduate school. And many of you are part of one of these 3 large NSF programs doing the lab course. And for some of the science results, kind of the leading science results, in addition to the gamma ray burst work that we've done, a number of years ago, we detected colliding planets in another star system. 2 planets actually ran into each other and blew themselves up, and we'll see that's actually quite common in the history of our solar system as well. Now, this is an artist rendering. We can't see stuff that far away in such detail, but it made a giant cloud of dust and debris that then orbited the star and blocked it periodically. And this was the most natural conclusion, most natural explanation of the data. Closer to home, we have discovered rings around objects other than the gas giants that was never known before. This is Chiriclo. Again, this is an artist rendering of Chiriclo. It's the largest object orbiting between the gas giants. And we have a group of people we work with that, for objects like this and new objects discovered out beyond Neptune, we wait until they pass in front of a background star. They're very faint and hard to see. So when they pass in front of the background star, it blocks the star's light. And it's basically casting a shadow on Earth that's moving across our telescopes. And by timing how long this takes, we can measure how big the object is super precisely. If you have many telescopes in the shadow, you can measure its shape. You can even measure if gases are coming off of it, not really an atmosphere, but something we call an exosphere. And this one surprised us because it had a little dip ahead of time and a dip after. And you combine this with the data from the other observatories, and it's clearly a ring, a double ring going around this world. And there have been 3 other objects like this discovered since. And then most recently, and someone asked me about this after class last time, in 2017, we discovered using these telescopes, the same telescopes you're using in the lab or will be once the Chile site reopens, the first visible light signature from a gravitational wave event. These are things Einstein predicted. You have 2 dead stellar remnants orbiting each other, getting closer and closer. He predicted that they'll be actually distorting the fabric of space and time itself. Pretty wild. We think of space as nothing, but Einstein described it as something that can be bent and distorted. And these waves then go throughout the universe, and they cause these kinds of ripples that are passing through us right now. stretching us this way and that way and this way and that way, but at a subatomic level. So we don't notice it. We don't see people going, you know, as they're walking around. But in theory, it's happening at a subatomic level. And so they've been building devices that can measure this. This is like national level. The US government's built 2 of them, one in Washington State, one in Louisiana, called LIGO. The Europeans have built one called Virgo. And they're tubes, 4 kilometers long. You take a laser, you split it, you run it down those tubes, they bounce off mirrors, come back and merge. If the tubes are the same length, they merge in a constructive way.
Professor?
Yeah, go ahead.
Earlier you mentioned like these things could be happening at subatomic level. What's the difference between atomic and subatomic?
Subatomic just means smaller than atomic. I'd have to look up how small the effect is. It could even be subnuclear. I can't remember, but very, very small. Yep.
Okay, thank you.
Sure. And so if they come back, if the tubes are the same length, they come back and interfere constructively. But as these waves go through, they make one tube longer and then that one shorter and the other one longer. Again, very small. You're talking less than the size of an atom over the scale of 4 kilometers. But we can now measure that, and they've been finding these merging objects, usually just merging very massive black holes. If you have 2 things that you can't see merge into something you can't see, then there's nothing else you can do other than trust this data. But we've been waiting for merging neutron stars, which are less massive. It's a weaker signal. And in 2017, they got their first and so far only observation of this. And they can tell from the signature what it is. And again, they have 2 sites so they can double check. It's not just some truck rumbling by or someone slamming a door in the lab, which can also create signatures if they're that sensitive. But this is the expected pattern of these objects going faster and faster and faster and closer. They merge and then it disappears. And they then tell us where to look. And it's not super precise. LIGO was able to narrow it down to this kind of light green region, and actually 2 light green regions on the sky. And that's a lot of sky to look at. The prompt telescopes, for example, and most telescopes, they're imaging just a teeny tiny piece of the sky. If I hold this up and look through this little hole between my fingers, that's about how much we're taking a picture of. So that's too much of the sky to search. Then Virgo came in, it's a little bit weaker, but they were able to tell us it's in here. And then a gamma ray signature came in. So these 2 neutron stars merged and basically made a different type of gamma ray burst. The gamma rays were coincident. And so we then searched every galaxy in this region, which took a while, but we eventually found it, and here it is. And here's an older image of that same galaxy where it's not there, so we knew a new object. And this is now called a kilonova, first ever discovered kilonova. It's the explosion you get when you merge 2 neutron stars, and they think that these things produce a lot of the heavy elements in the universe, like uranium, plutonium, things heavier than bismuth. So it's a whole new field of research. Anyway, we've done a zillion other things as well, but I just wanted to highlight some of the stuff, tell you a little bit. Since many of you are using the telescopes, and just also because I'm your professor, you may be interested in knowing what I do with my research career. Anyway, the every scopes. Let me tell you a little bit about Professor Law's work. This is just a brilliant idea. This is in Chile. I gave up one of my prompt domes so he could put it. I didn't give it up, he pays for it, but he's leasing one of my prompt domes and put this mushroom-shaped thing in here. It's not every, it's every, E-V-R-Y. Tele is Latin or Greek, I forget which, for far. So a telescope is a far seer. Make sense? Every, E-V-R-Y, is, again, Latin or Greek, I can't remember which, for wide. This is a wide seer. He's basically mounted a whole bunch of little telescopes on this structure, and it maps almost the entire sky that's available to it every 2 minutes. And it doesn't see as faint, as deep as other telescopes, but it goes pretty deep. And it's a tremendous amount of data that you're recording every 2 minutes. I mean, it's terabytes of information nightly, petabytes of information as well, you know, over time. And he's looking for things that change, things that go bump in the night. and exoplanets in particular. So he's monitoring all the stars in the sky that he can see, which are quite a few, just looking to see when the brightness dips. If a planet passes in front, if it's aligned just right, passes in front, the brightness can dip, even just like a fraction of a percent. But then, there's something there. And if you keep monitoring it, catch it again and again, you can figure out the orbit of that planet. So he's discovering worlds around the nearby stars. And probably the first planet that humans eventually venture off into space and visit around another star will be picked up by discovered by either the Everyscope or its follow-up mission. So there are two of these Everyscopes, one in Chile now, also one in California, but he's just got funded to build the next generation, which is called the Argus Array, which is a nerdy Star Trek reference. And this will have basically 650 0.2 meter telescopes, so 20 centimeters like this. 650 of these mounted on this large dome that just moves with the sky and images everything every couple minutes. So those are the small telescope efforts going on at UNC, which are pretty cool. Okay, so that's it for UNC telescopes and for optical telescopes in general. Any questions? Okay, I just figured, I'm not going to test you on, do you know our telescopes? I may use them in examples, but I figured you may want to just see them and see what's going on here. Okay, let's move out beyond the visible part of the spectrum, or sometimes called the optical, visible optical. You can use those words interchangeably. So here we have a plot of wavelengths, small wavelengths on the left, so these are the high frequencies, long wavelengths on the right. I normally plot this the other way around, but this particular figure is plotted with wavelength increasing instead of frequency increasing. And what it's showing you is the opacity of the atmosphere, what light makes it to the ground. This determines what astronomy can be done from the ground and what astronomy has to be done from space. So let's pull up the doc cam as well and make some, I'll describe and then I'll write it down. So here you see the optical window, and as we move off into the ultraviolet and the X-rays, nothing makes it through. And that's good because ultraviolet and X-rays, gamma rays, they can damage our skin, give you a sunburn, and if a lot of the higher energy stuff makes it through, you'll get cancer. So it's good that it doesn't make it through. It's blocked by the ozone. That's why the ozone is such a big issue, or at least it used to be. The ozone problem is mostly fixed. It's totally different from global warming. Don't get the two confused. Ozone's like a little baby practice problem that we've mostly solved. Global warming, the emission of carbon dioxide and methane, that's a whole nother ball of wax. And we'll talk about these when we talk about the Earth as a planet. But anyway, ozone protects us, but it makes it impossible to do high energy astronomy from the ground. You got to go to space to do that. As you move into the infrared, carbon dioxide becomes a problem. And most of that is naturally occurring. We are putting up some of our own as well. But either way, there is carbon dioxide in our atmosphere, released when we exhale. That hasn't been taken up by plants yet. There's some natural balance, and that makes it hard. There are certain bands here in the near infrared that we can still observe, and then moving out to the mid infrared, but after that, nothing. And it's not just the carbon dioxide, but water vapor. And unless you're in a desert, there's going to be water vapor in the atmosphere, and that blocks you in the far infrared. Definitely have to go into space. But then as you move up into the microwaves, which is a form of radio, short wavelength radio, then you recover, it does come through the atmosphere, basically oxygen, and can't get rid of the oxygen. That's a good chunk of the atmosphere. But oxygen blocks you here, but the longer wavelength you get, then it comes back through all the way to the ground. So we have another ground-based window, and then longer than about 20 meters or so, the waves just kind of skip off the atmosphere and they bounce. We're reflective, and they don't come in. So I said all that in words. Let me just write it on the dot cam real quick so you have that information. So in the ultraviolet X-rays and gamma rays. The problem is ozone. In the near infrared going through the far infrared, the problem is carbon dioxide and water. And then from the far infrared through the long wavelength radio, problem is water and oxygen. Sorry, that's supposed to be short wavelength radio. Far infrared through the short wavelength radio. Then the radio is good. You could do that from the ground. The visible is good. Could do that from the ground. And then you have the long wavelength radio, and we're reflective. So you would have to go to space for that. No one actually does that. But for these others, the high energy stuff and the infrared stuff, we do go to space. Now I'm going to talk about the radio in class today and get as far as I can. And anything I don't get to, I'll assign. But the space-based stuff, I'm assigning that as a separate video. And I'll show you that stuff at the end of the lecture. So let's jump into radio and see what I have next. Right, so radio's very cool. There are a number of similarities, of course, because it is light. It's just long wavelength light, but a number of differences as well. For example, you can do it during the day. And here's our picture of why the sky is blue. The short wavelengths scatter all over the place. The longer wavelengths scatter less. So if you go longer and longer all the way out to the radio, they don't scatter at all. It's like we have no atmosphere. There's no atmospheric blurring. The sun is super bright, but the rest of the sky is dark. You can see the sun and you can see everything else as well. It doesn't scatter the radio light all over the place, making the sky radio bright. So you can do it during the day. You can do it through clouds. It can be cloudy, the radio waves come straight through. You can do it during the rain. And that's, for Earth conditions, but also it penetrates dust. The radio waves are longer than the dust grains are big, so it can go through dust. And dust is a huge problem in the optical. Here's a picture of the optical sky. Here we see the galaxy, and all these black regions, those are lanes of dust blocking our view. And even the stuff we can see, we're only seeing the nearby stuff. The faraway stuff is obscured by dust. But let's zoom into the central region here. Here it is in the optical. Here's the plane of the galaxy. The galactic center is right in here. But you see the dust is, now here's the galactic center. The dust is blocking what's going on in the middle. If you look in the radio, that's the brightest region. Most of the stuff is happening behind that dust. So it allows us to peer into the centers of galaxies. In particular, at the very center of our galaxy is a supermassive black hole, but kind of on the low mass side. It's 4 million times the mass of our sun. And we know that because this is just a drawing. We can't see it in this detail, but there's a disk of gas that we can observe in the radio, and we can measure the Doppler shifts and figure out how fast it's moving. Also, other stars in the vicinity are orbiting it, so we can do Newton's form of Kepler's third and figure out the mass of the central object. And so there's an object there that's 4 million times the mass of the sun. And the only thing that we know that could be that massive in such a small space would be a black hole. And the black hole has this disk of gas, and some material shot out in these jets, and some of it, the disk of gas is glowing. Eventually it falls into the black hole. Now,
Where did you say this is located?
This is the center of our galaxy, and the center of all galaxies will have a black hole. Once one forms, there's so much material at the center of a galaxy, it just gobbles it up, gets really big. So a million.
Dr. Rickert.
Yeah, go ahead.
So I had two questions actually.
Yeah, go ahead.
So first, when you're taking a picture of something in the galaxy that's really far away, how do you know if the object is just super far away relative to other objects, or if it's smaller relative to other objects?
You don't. And so distance is the trickiest thing to measure in astronomy. And there's a whole bag of tricks for doing it. In fact, it's the organizing theme of Astro 102. It's the organizing theme of the rest of the lab. If you're in the lab course, you're doing parallax this week and next week, then you're going to use these things called standard candles to measure distances farther out. And we can use these standard candles to figure out how far away the center of the galaxy is.
Okay, and my second question was, isn't it true though that black holes can eventually disappear? So like what happens then?
Yeah, in theory, according to Hawking, black holes do emit particles on their boundary. It's a strange quantum mechanical process where they're not really emitted, they kind of form there, and positive mass flows out and negative mass flows in, negating the black hole. And it's never been observed in practice, and we shouldn't have. It's a very small effect. It becomes bigger and bigger near the end of a black hole's life. But they should eventually evaporate. We're talking very, very long time scales, though. Well, you probably saw the news reports about a year or so ago that we finally observed a black hole and saw the event horizon. We see lots of black holes, but really we're just observing the accretion disk around it. You can't see the black hole itself because the event horizon, the dark region from which not even light can escape, is very small. But we were able to achieve this. I'll get back to this picture in a second. I forget exactly when it was, about a year or two ago. And this is not from the center of our galaxy. They tried that, but they had this is a very technically challenging observation to make, and it didn't work out. They're going to try again. This is actually from a collection of radio telescopes spanning the entire globe, working together as a telescope as big as the entire planet. Something called interferometry, which I hope to get to, but probably won't, but we'll see. So let's take a look at it. Let's see if they're doing maintenance on my radio telescope. I don't have a global network of radio telescopes, but I do have one radio telescope. And I just showed you a picture of it, actually. Let me put that back up for a second. So we have this radio telescope integrated into Skynet. It's, I gave you the basic specs. The dish is 20 meters across. It's huge and heavy, and if you're in the lab course, you'll get to use it. And at the beginning of the last recession, there was a stimulus act, and I was able to raise about $2 million to expand Skynet. I tend to do well when the economy crumbles because they stimulate the economy, and I always find a way to get a piece of it. Anyway, I refurbished this telescope in West Virginia, and it has many similarities to optical telescopes. It moves along two axes. It can point anywhere in the sky, though it has some differences as well. Notice the mirror. It is a parabola, so that's a similarity, but it's not shiny. And the difference is your parabolic surface only has to be smoothed to about 1/10 of the wavelength. And with optical telescopes, that wavelength is, hundreds of nanometers. So it has to be smoothed to tens of nanometers, which means it has to be shiny like a mirror. But here in the radio, this telescope normally looks at 20 centimeters. So it only has to be smoothed to 2 centimeters. And so I don't need to polish it. I can take sheet metal. I didn't build this, but you can take sheet metal and bend it, and as long as it's parabolic to within 2 centimeters, it will bounce radio waves. So, it's similar, but they're not shiny. And the other big difference is up here at prime focus where the light collects, the light is 20 centimeters across. And so that's the size that your pixels have to be. If you want to put a camera up there, each pixel has to be this big, and there's not enough space for it. So radio telescopes use single pixel cameras. We don't point, shoot, and have a picture. We point and just take a reading of how bright the sky is at that point. If we want to make a picture, then we have to keep moving it around. We kind of do a raster pattern, and it takes time to bring it in. At least with a single radio telescope by itself, that's how you have to do it. So let's take a look at that. See that black hole that I just showed you, that's from Virgo M87 at the center of the Virgo cluster. That's the cluster that we live in. It's a cluster of galaxies. We live in the outskirts. At the very center, there's a galaxy there, big galaxy, gobbling up other galaxies, and this black hole has grown from millions to billions of solar masses. So that's why they targeted it. Being so massive, the event horizon was big enough to resolve. So I'm going to go to Skynet Live and just see if my radio telescope's connected. It is, so hopefully they're done with the maintenance. And hopefully this isn't, I think it would show if it's disconnected. Let's find out. So I'm going to go to radio observing. I'm going to add a new observation. And it is right here. It's Virgo A. There you can see that's an optical picture of that cannibalistic galaxy. It's up right now. It's very close to the sun, actually. Picking my frequency. And since it's a single pixel, I have to pick the pattern that I want it to move through. And I'm going to pick a daisy pattern. I'm not going to raster and make a full picture. I'm just going to do a few loops across it. So the loops will have a radius of 180 arc minutes. I'll do 4 loops over the course of 2 minutes. Let's save and continue. And I'll submit it. And we'll go to Skynet Live. And it should take about 10 or 20 seconds to be picked up, as long as the telescope has been reconnected. While it's thinking about that, I'll just go, oh, there. Nope, too bad, mount not ready. So they're doing the maintenance work. Well, I'll try this demo in the next class as well and get it on the recording, or maybe what I'll do is I'll do it at the beginning of the next class, because it is fun to see. I built up your expectations and then we're disappointed there, but I will show it to you. Let's use our 10 minutes to wrap up radio telescopes, single dish radio telescopes. What I can show you actually is, let me bring this back up here. So this is if you use a radio telescope the size of the planet, hooking all the radio telescopes together. If you do use this telescope that we're just attempting to use, and you do a raster pattern, getting data from each and every pixel and put it together, you see something like this. It's not very detailed, it's blurry, and you calculated that at the beginning of the class. Since the wavelengths are so large, the blurring of the telescope is also quite large. And you know, you use the optical equation for that. Let me give you another equation for it. The two equations are equivalent, just the units are different. This may be easier to use in the radio. The blurring scale is 40 arc minutes times the wavelength measured in centimeters. Because radio wavelengths are usually given in centimeters times the diameter measured in meters. And so for this telescope that we're just looking at, it's 40 arc minutes. We're looking at 20 centimeter radiation. It's a 20 meter diameter telescope. And so we're talking about 40 arc minutes, which is almost 1 degree. And again, in the optical, you're used to much smaller diffraction limits, but in the radio, 1 degree, it's huge. It's like me taking off my glasses and looking at you. What I could tell is, those of you with your video on, you have faces. Yeah, those are faces. Eyes, nose, mouth, those are just theoretical concepts when my glasses are off. And observing with a single telescope in the radio, that's how it is. The only way you can beat that is by using larger and larger telescopes. And so that's kind of the theme with radio telescope construction. I have another PowerPoint up here. Yeah. So let me show you some of these larger telescopes. I'm trying to grab the edge. There we go. Pull it off here. So there aren't too many, so I'm just going to run through the ones that exist, or used to exist anyway. This was the first very large radio telescope. They built it at Green Bank, and you don't have to remember the names of these, I'll just tell you. It was called the 300 foot because there's 300 feet across, the size of a football field. And they built it in 1965, hoping that it would last 5 years. They didn't have enough money to do a good job. They took a number of shortcuts. It only moves north and south. It doesn't point east-west, so you have to wait for whatever you're looking at to pass overhead. You crank it to the right angle. was too expensive to build high enough off the ground, so they built it low and just dug a ditch. So when it had to look down near the horizon, it went half underground. And in other shortcuts, and they really expected it to only stand for 5 years. Given that, I don't know why they built the control building underneath it, since they were expecting it to fall down. But it lasted to the late 1980s, so they really got their money's worth. And then it fell down on the operator. Yeah, it was his first night on the job, or at least that's the rumor. I've actually spoken to him about it, but the building held. He was fine. One I-beam came down through the roof next to him, and then he went out and took a look, and the whole scope had collapsed down to that. So after that, Congress approved money to build a replacement, and it's called the Green Bank Telescope, the Robert Sieberg Green Bank Telescope. He was the senator from West Virginia who got the money through. Here it is being built, and this is an animation, but it's animating on the other screen. So just showing you how it moves. You'll just have to take my word for it. And here it is at night, all lit up. And this is, it's interesting in a couple ways. First of all, it has an active surface. There are about 2,000 panels, and there are pistons under each one. So every time it moves, it morphs itself back into a perfect parabolic shape, just like active systems on optical telescopes that we talked about. It's also open aperture. Other telescopes, you have your receiver here, and then you have these support arms holding it. And those support arms can mess up the light. The radio light diffracts around them as it comes into the telescope. So what they did is they envisioned a telescope 600 meters across where the receiver would be here, and they built just this piece of it. And so it's called open aperture. The light comes down, bounces off the primary, comes over to the side, hits a secondary here, and then goes into a room where they can change the detector to observe different wavelengths. Now you can go bigger than this. I'll just run through these larger ones quickly. This is Arecibo in Puerto Rico. It is 300 meters across. So this last, Green Bank is 300 feet. This one's 300 meters across, so much bigger. They found a valley the shape of a parabola and hung a net. It doesn't move, it just looks up. They have some flexibility. They can pull the receiver towards one side or the other, kind of like the SALT telescope, where you pull it to the side, use a part of the dish to look in one direction and vice versa. So maybe about a 10-degree swath across the sky. And this was built in the 70s, and very powerful telescope. And recently the Chinese built a similar structure called FAST. It's an acronym, I forget what it stands for. It's 500 meters across, and that just went into action. But if you want to get bigger, you have to do a science called interferometry, which is a way of piecing together different telescopes. And I have a short video on this that I'm going to assign to you to watch along with the space video, but let me just show you some of them here. In the video, you'll see how they work, but I'm in my final few minutes. These three telescopes, also at Green Bank, here's the 300 foot before it fell down. This was the prototype system. They act together. They have the same light gathering power as three small telescopes, but if you hook them up correctly, they have the resolving power of a telescope as big as their spacing. And it's a tricky science. You don't just point and shoot. You build the image up piece by piece, slowly over time. You have to move the telescopes through different angles, and Earth's rotation does that, and different spacings. So they're actually on tracks, and you can move them close together or far apart to build up the different image components. Once that was pioneered, they built this, the VLA, the Very Large Array. Again, our acronyms aren't that creative. In New Mexico. You might have seen it in certain movies. And this is its compact configuration, 27 dishes, and they can also be stretched out along these train tracks over the scale of a kilometer or so. More recently, we've built a short wavelength millimeter version of this called ULMA in the high Chilean plateau, Atacama Desert. And this is kind of the leading radio effort in astronomy today. The leading ground-based optical is that Rubin telescope that's going to map the whole sky every 3 days. The leading radio effort is ALMA, and the leading space-based effort is Webb, the replacement for the Hubble Space Telescope. Those are the three big observational efforts in astronomy. So that's the radio one. And you can hook them together across the entire world. You can't run cables, so you save it to tape with careful timestamps, and then the tapes can be brought together and the signal synthesized. So there are two of these. One's called VLBA, Very Long Baseline Array. It's basically all the US major radio telescopes from Arecibo in Puerto Rico all the way to Hawaii. Acts as a telescope as big as that region. You can also hook up the entire planet. That's called VLBI, Very Long Baseline Interferometer. It's an international consortium. It's not used as much because it's harder to get everyone to work together and cooperate, but that's what they used to image the black hole. And you got to collect the data for weeks and months and get all those telescopes to work together that long. But here you can see they image the event horizon, and this is the disk of gas around it. All right, so we are a minute over, but I just want to show you on the YouTube site what videos we're talking about here. So going into lesson 4, I'll post today's video after this one, after this last one that I posted. And then I have some optional videos and some mandatory videos. If you want to learn more about radio astronomy, these first 2 videos are there. They're optional. I talk about the history of radio astronomy here, and the first half of this radio telescope one is also kind of talking about the history, and then it picks up with the 300-foot and the Green Bank telescope and what I talked about today. So this one and the first half of that one, if you want to learn more about the history of radio astronomy, this 9-minute video is about interferometry in the radio and how that works, and then there's this video on space-based telescopes. So for the homework, definitely watch these last 2. And although I'm like 2 minutes over, I should just go to one more slide here and mention, for those who are interested, I do run a summer program at the Green Bank Observatory in West Virginia. I take 18 students from across the country. There's an application for it, and I'll send that application around in probably January, and I have all your emails. I'll email it to you then. And applications are due in March, and I've been doing this every year since 1992, except this past year because of COVID. It's just super fun. If you're gonna be a major or a minor, or you just have a real interest in astronomy, this is a cool program. You can get EE credit for it, and you need that to graduate. And you work with other students from across the country. And we have 2 telescopes, the one that's pictured, which is 40 feet across, and the very next morning after you arrive, you're on the telescope using it. It's a fully manual telescope. It's not computerized. You make it work manually. And we do observations of all sorts of cool things, and you also use the 20-meter diameter telescope through Skynet. It's a week-long, 24/7 crash course in radio astronomy, but lots of fun if you're into that kind of thing. Anyway, I went 3 minutes over. Apologize for that, but I'll stop and stick around for questions.
Thank you, Professor.
Thank you.
My
Have a
pleasure.
good weekend.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Dr. Hart.
My pleasure.